Log on, tune in, find out. Another good idea from Cambridge.
Let me introduce today's speaker, Russell Cowburn, whom I knew when he was an undergraduate here in the early 1990s at St John's. He did a PhD jointly between here and Paris. And then he was a junior research fellow at St John's, and he's worked on nanoscience, I guess, most of his career. He was a lecturer and reader at Durham, then he went to a chair at Imperial College before Cambridge managed to seduce him back, as it has a habit of doing, I'm afraid. Well, no, I'm very pleased, not afraid, with professors. And he's just started this term as full-time Director of Research at the Cavendish Physics Laboratory. Besides all that, he's also run 2 startup companies, both concerned with nanotechnology-related products. And his current research, he tells me, is finding ways for computers to store thousands of times more data than we currently can. Well, for any of us with digital cameras, I guess that's good news, because it seems to fill up my hard disk in no time at all. So it will have a very practical and useful application, I'm sure. But today, as you can see, Russell's going to talk about nanotechnology, religion and ethics. The last thing I didn't tell you about him is that he's just been elected to as a Fellow of the Royal Society this year at a very tender age, so we should give him his congratulations for that as well. Over to you, Russell.
Great, well thanks for the introduction and thank you for your warm welcome. Right. Okay, here's what I've got. I'm assuming that this isn't a room full of physicists, so those of you who are, please be patient with the slightly slower pace. But I'd like really to try and communicate from a practitioner's point of view what exactly nanotechnology is, so what it is, how to do it, just so that you get a really good feel of what exactly is it that we spend our days doing. And then really ask the important question, why the fuss? Why is nanotechnology such an important area, and why has it been so marked in the last 10-15 years? And then very practically, how will it change our lives? This isn't something that's going to remain in the laboratory. I'd like to try and give you a flavour of some of the areas that you will end up using nanotechnology, both already today and in coming years. And then, after a fairly happy picture, I'd like to introduce a more radical view of nanotechnology, some of the noises off stage that have been happening, and that might explain why there's been a little bit of discussion in the media about how desirable this is. And then turn from there into just trying to explore a little bit. And I'm by no means a social scientist or an ethicist, so it'll be very much an amateur level, but just trying to explore some of the ethical implications of that, and finish off with a few thoughts that I'm a practicing Christian, how I see this fitting in with my worldview as a Christian as well. So, what is nanotechnology? This, it's all about sizes. So this is a size scale going from a metre, and then each of these is a factor of 1,000 down, so a millimetre is a 1,000th of a metre, then a micron is a 1,000th of a millimetre, and a nanometre is then a 1,000th of a micron. And if we just populate that with some of the things we're familiar with, well, at the metre scale, it's you and me, we're all a metre something. We know what a millimetre is, that's still well within our sphere of reference. Once we get smaller than that, we begin to struggle a bit. So the mid 50 microns or so, that's a human hair, so there's a human hair on a pinhead with alarmingly a couple of dust mites next to it. But remember, in the world of nanotechnology, this is still enormous. This is still 50,000 times bigger than the nanoscale. Red blood cells, 10 microns or so. And then at the very bottom of the range, we've got the atom. The atom is less than 1 nanometer in size. Nanotechnology is everything that lies between these two limits. So it's typically bigger than an atom. An atom delineates the smaller size, and then we go up to just beneath a micron as the largest size. So that's the area, that's the space that nanotechnology exists in. Just to give you a flavour, I'm going to show you an awful lot more of this sort of stuff, but this is one of my favourites. This is the world's smallest calculator. It's actually an abacus, so you know it's the classical meeting modernity here. But each of the beads on the abacus is a single molecule, and you can see that using a very sharp tip, they've been pushed along a non-existent rail in order to count from 1 to 10. It was actually IBM in Zurich who did this, and you can well imagine what the press releases were like. You know, IBM builds the world's smallest computer, and so on. Well, that's what it looks like. let me just talk a little bit about how we do it. These are some of the techniques of nanotechnology. Probably the most famous, the most influential one has been the atomic force microscope. It's really simple. It's analogous to the way a blind person reads Braille. So you just have a finger. In this case, you make that finger near atomically sharp, and you put it on some sort of spring, a little diving board, and you arrange some means of telling whether that diving board has moved or not. So normally you fire a laser off the top, and if the cantilever moves up and down, then that laser deflects accordingly. And it turns out this is remarkably sensitive. Just by dragging that diving board with sharp tip across a surface and watching how it goes up and down, you can actually see the individual atomic corrugations of the surface. You can see atoms by that very, very simple method. And just to prove that, here's a picture of silicon atoms on a surface imaged by this technique. And you can actually see they form this little circular so-called reconstruction. And you can even see the places where there are missing atoms and things like that. So actually a very, very simple technique that, although developed initially by physicists, has found use in material science and biology, because biologists like to take these tips and stick them inside cells and see what's going on in there. You can even pick up a strand of DNA on the end of a tip and yank it and see how stiff it is. All sorts of remarkable things across a whole range of modern science. Most nanotechnology is done in machines like this. So this is from my own lab, and shiny, big silver machines is the order of the day. And one of the ironies of nanotechnology is that the smaller you get, the bigger the machines you need to actually control it. So, and the point of all these is really to make perfect nothingness. We want vacuum as good as vacuum can be. Largely because if you're only an atom or so in size, if a passing air molecule just travelling around as they do happens to bump into you, that's actually quite a major deal. That's a big collision. And so you want to get down to a level of vacuum that is so pure that there's virtually no probability that a passing residual atom or molecule will hit you. It's more likely to hit the sides of the chamber and get stuck there than it is to actually hit you in the middle. So that's somewhere around 14 orders of magnitude lower pressure than atmospheric pressure. So there's only one particle for every 10 to the 14 that we have here. Another technique is lithography, and it has many flavors. I'm showing you electron beam lithography here. And this is what people refer to as the top-down approach to nanotechnology. There are two ways of getting at very small things. You can either come in from the top and use delicate instruments that are in and of themselves large to try and scale down, or you can come up from the bottom and try and, that's more the approach that chemistry and material science comes from, where you actually control the behavior of the atoms from the very start and let them build from the bottom upwards. So lithography is the classic top-down technique. And there you run an electron microscope back to front. Instead of using it to look at things, you use it to draw things. So you program the computer with the structure that you want to make. The computer grabs the electron beam and draws it out, and you make sure that you've got effectively an old-style photographic process in place, so that wherever the electron beam goes, that causes some chemical change that ultimately ends up in matter being deposited there. Just to give you an example of that, here is a Friday afternoon experiment. That is part of the Encyclopedia Britannica written out on a piece of silicon using 20 nanometer pen strokes. And we can read it, it's quite clear. Let's just look at so those are some of the main techniques. Let's just look at some of the materials of nanotechnology. So all the forms of carbon are really classic nanotechnology. So one of the most exciting is carbon-60, so-called Buckminster fullerenes, named after the geodesic domes that the architect created. And these are like footballs of carbon. It's a new allotrope of carbon. So at school we're taught that carbon comes in the standard allotropes of graphite and diamond, things like that. Well, C60 is a different allotrope where the 60 atoms form together into this football-shaped molecule. And that, Harry Kroto got the Nobel Prize for that in the mid-90s. But there are other ways of doing that. So you can do what's effectively rolled up chicken wire. So you can make what's called a carbon nanotube, where instead of being this zero-dimensional object, you have a one-dimensional object like this, where you form this long tube. And these can be many microns long, which on this scale is extremely, extremely long. And then very recently, the Nobel Prize was just awarded a few weeks ago for this in physics to colleagues at Manchester. There's the two-dimensional form, which is graphene, where you just take a single layer of atoms of carbon and you end up with this two-dimensional sheet, which has really quite remarkable properties, both in terms of strength and electrical conductivity and all of these things. So these three allotropes of carbon are really at the heart of a lot of nanotechnology. An area that I'm personally very interested in is magnetic materials. It turns out that magnetic materials behave very differently when you structure them on the nanoscale. So these are all the same physical element. These are all an alloy of nickel and iron. But by using the electron beam lithography, we've structured them into different shapes, be it little hexagons or triangles or wires. And the interesting thing here is that they all have very different magnetic properties. That no longer are the magnetic properties just dictated by the elements that you're using, but also the size and the shape of the structure that you've made begins to play a role. And that's very important, and that's really beginning to exemplify the reason that nanotechnology is so exciting, because of this extra degree of freedom that you get. There's a related area that you should be aware of called MEMS. People argue as to whether this really should come into nanotechnology or not, but it's all part of a continuum. And this is micro machines. So these are there's a scale bar of 50 microns, just to give you an idea. And at that scale, it's still possible to make classical Victorian type machines with cogs and pulleys and things like that, using lithography. So you draw the shapes that you want, and then you use a photographic process to transfer those into something like silicon nitride, and you can really make proper little working machines. And most of us here who drive a car will use these on a daily basis. The airbag in your steering wheel senses the sudden deceleration of impact by a little accelerometer made through micromachining. And because it can all be made on a silicon chip, it's very cheap and easy to integrate and doesn't need careful setting up and is therefore very reliable and very cost effective. And a very important nano object is the quantum dot. So this is a very small scale picture. This is just 50 nanometers across. This was taken by one of the variants of the atomic force microscope that I showed you. And you can actually just see on the surface here, you can see the atoms, the individual atoms that make up this little square-based pyramid. And what you typically do here is you either introduce a little defect into a strained material, or you put two materials very close to each other that have different lattice constants, and so you introduce stress into the system. And that stress wants to relieve itself by popping out and forming this little pimple. But that pimple, from a physics point of view, is a confined object. It's a little zero-dimensional object. And so, for example, the colour of this is very different to the underlying material. And you can use this to, for example, to make security tags to put into banknotes, like a super version of the ultraviolet light that the bank teller uses to check if your notes are genuine. Well, this will only respond at a very specific wavelength, with a very predetermined way, and so you can check the authenticity of things using structures like this. Or you could use these, for example, to highlight cancer cells if you attach a biomolecule to them that will bind to cancerous cells. So a huge range of potential applications for quantum dots. And then I guess the ultimate in nanotechnology is the atomic or molecular manipulation. And that's where you use those very sharp points of the either the scanning tunneling microscope or the atomic force microscope, and you push atoms around one by one to build what you like. So this was a very famous example, again from IBM, where they pushed iron atoms on a copper surface to form this circular corral. And you can see work in progress. So this is the job, a quarter done, some random atoms, and they were picking them up one at a time and moving them to where they needed to be. There's the job half done, 3/4 done, and that's the finished job. The Japanese competitors were doing the same thing, and they actually wrote out in kanji the word atom. That's probably a joke that's lost to most of us here, but apparently that says atom. And as well as being a really fun thing to do, and you can do crazy things like calculate what the effective density of data storage or density of writing would be. And it turns out you could fit all of the books of the British Library into a postage stamp and all this sort of ridiculous notions that you would never even want to do. But there's some very interesting physics coming in, which is where the nanoscience and nanotechnology go hand in hand. That you might think that is an extra atom they put in the middle, but actually it's not. It's a ghost atom, and it comes from the interference of the electron wave functions coming out of all the individual atoms. And this gets us into the world of quantum entanglement and teleportation and all these things that really are on the brink of Star Trek, to be honest. Okay, so I hope that's given you a little flavour for some of the fun things that we can do. Let me just try now and identify why I spend most of my time playing with this stuff. Well, it's really, from a scientific point of view, it's the properties of materials are different for such small objects. The first version of these slides, I wrote that the laws of physics are different, and it's not true. I mean, the laws of physics are universal, and they're unchanging. But the way those underlying laws manifest themselves in a given material system is dramatically different if that system is structured on the nanoscale compared to if it's just a bulk system. And there are three real reasons for that. The first is a very simple one. It's a large surface area. So the analogy is given, think of a football and compare the surface area to volume of the football, and then think alternatively of a collection of golf balls put together to make the size of a football. The collection of golf balls has a much bigger surface area, because not only do you have the outer perimeter, you've got the individual surface areas of all of the constituents. Extrapolate that down to the nanoscale, and you can make materials with enormous surface areas the size of football fields in a tiny volume. And if the physics of the way the material behaves is driven by surface area, as it is, for example, in catalysis, then you've changed the way that material behaves quite dramatically by structure. Another reason is to do with quantum properties or internal length scales. Most of us live our lives in the classical world, but those of us that are physicists know that underneath that there is a whole quantum world, which is largely inaccessible to our everyday experience. But if the material you're working with has been structured on such a small scale, then it's living deeply in that quantum world, and so it behaves in a very different way to the bulk material. The flip side of that is that sometimes materials have a certain length scale, be it the wavelength of the electron or the length scale on which two forces balance. In my world of magnetic materials, that's very much the case. And as soon as you start playing around with the material on a length scale that's comparable to one of those internal length scales, you begin to perturb it very badly, and it's modified quite dramatically. And then finally, again, it's a bit of a physicist thing, but dimensionality control. If I make my graphene sheet just one atom thick, then that is a true two-dimensional system. And all the laws of physics, the equations underneath them, solve differently in 2 dimensions than they do in 3 dimensions. And so an electron living in a 2-dimensional world, as in an electron, one of the carbon atoms in graphene would, feels very different to an electron living in a bulk material. So that's really why the world is different on the nanoscale. Why do we care? Well, hopefully, with that understanding we get from nanoscience flows nanotechnology, in which we can access new properties in order to build better, cheaper, smarter, cleaner products. That's the driving narrative for a lot of this work. So what do they look like, those better, cleaner, smarter materials and properties? Well, you see them in computing, you see them in healthcare, you see them in renewable energy, you see them in sport, don't know anything about that, you see them in clothing, and interestingly, you see them in food. I'll give you a few snapshots of some of these different areas. This list is by no means exhaustive, it was just the first I could pull together. In computing, I mean, it really is remarkable how things have changed in computing across the last century. So that's what a transistor looked like in 1947. And this is a bench-sized object. I mean, this is a big nut and bolt, and it's like this. And essentially, it was a big lump of, well, a big mechanical support, and then a lump of semiconductor and a contact driven into it, by the looks of it, with a hammer and nail. And this was the first working transistor. This is what a transistor looks like today. So this is the transistor itself. This smallest part is only 65 nanometers across. And essentially, it's using exactly the same operating principles as transistors have for the last 30 or 40 years. Nothing's changed fundamentally in the physics. We've just managed to make them an awful lot smaller. And so that's why now you can pack a 300 millimeter wafer with transistors, with billions of transistors, in fact, and make latest microprocessors in a way that you never could in the past. So already, nanotechnology is deeply embedded in computing. Your iPhone has a microprocessor in that is a nanotechnology-enabled device, as does the Pentium in your desktop. So we shouldn't think of nanotechnology as being something that is coming in the future and might be a bit scary. It is absolutely here, and you're using it every day without even knowing it. Just to zoom in a little bit, one of the interesting things is one of the limiting steps in future development of transistors is how thin you can make a particular layer of insulator called the gate dielectric. And people are now engineering those down to the nearest atom. So you can see here, this is a cross-section of this part here, the insulation between the gate and the channel. So we just zoom in on there. You see that people have engineered it to the nearest atom. You can see the individual silicon atoms, the individual hafnium oxide atoms, and then a tantalum nitride cap on top. And it's that level of control that's being rolled out on an industrial scale. Intel manufactures billions of these every day, really without too much trouble. Healthcare is another huge area. This is just some very recent work I picked from my colleagues at the London Centre for Nanotechnology, just published a few days ago. So this is using one of those diving boards, one of those cantilevers that was developed for the atomic force microscope. But instead of using it to do microscopy with, they're using it as an ultra-sensitive stress sensor. And they're using it to investigate antibiotic-resistant bioforms, is probably the word I'm looking for. So they want to understand when an antibiotic tries to attack some bug that it seems to struggle with, things like MRSA, these hospital-acquired infections. Exactly how does it do it? What forces are at work? And what is the physical property of the bug that makes it so resistant to the antibiotic? And so by conducting the experiment on the back of one of those little cantilevers, and you can see the laser just firing in there, looking for any slight deflection in that cantilever, they can actually measure directly the forces between the antibiotic and the bug, and can work out how good a job the antibiotic is making of grabbing a hold of the bug itself. And it turns out that's one of the things that makes MRSA so resistant, is it's lacking one hydrogen atom, which makes its surface much stronger and much harder for the antibiotic to actually get a grip of and to start attacking properly. And they can do that by measuring the deflection of those cantilevers. So very real-world problems being addressed in a very sophisticated way. And the whole world of moving diagnosis from the path lab, from the hospital, to the bedside, and even ultimately into the pocket, is very much being driven by nanotechnology. So it's related to an area called microfluidics, which is also a sister of nanofluidics, where people make little chemical laboratories with pipes and channels to move liquids around on a chip. So there's a chip. This is sort of millimetre size, and these channels are micron size. And then they can have individual little droplets running through these and treat them really like a little conveyor belt and perform all of the analysis and testing that would normally go on in a hospital laboratory, but on a chip. Big role for nanoparticles in directing the focus of therapy to the place that it's needed. So for example, in cancer therapy, there are some great cancer cell killers out there. It's called chemotherapy. The trouble is it kills everything else as well. What people really want to do is to be able to focus the potency of that chemotherapy just into the cells that are cancerous. So this is a physical effect. This isn't actually chemotherapy. This is a physical effect where people coat nanoparticles of gold with an antibody that only binds to cancerous cells. And our biotech friends know how to do that reasonably well. And so you inject these nanoparticles into the bloodstream, and they run throughout the body and are completely inert, except with regard to cancer cells. And with those, they bind very tightly and surround the cancer cell. You then illuminate the patient using infrared light, which can pass straight through the body. And it turns out that because of their nanoscale properties, the gold nanoparticles absorb infrared light very strongly. So these little nanoparticles suddenly become red hot and either physically burn out the cancerous cells, or they can be used to activate a drug. If you have a chemotherapy that requires a little bit of temperature rise to activate it, you can just activate it locally in the area. So a lot of work like this, of targeting drugs, targeting potency of toxic chemicals just in the places that are needed. And some work in my own group of using little microstructures containing nano layers of magnetic material. There's a barcode, a little nano barcode, with a little landing platform on top where you can do drug exploration, so drug development. And when you get something that works, when you find a combination that attacks the thing you wanted to attack, you can tell which one it was by the unique barcode that was written into the little nano structures underneath. Renewable energy is an area that's very fashionable, very important. Prof was just reminding me about the need to offset my carbon in driving from London to Cambridge every day. And the list is just too long to go through in detail. But all of these areas are just potential applications of nanotech to renewable energy. I'll try to show you one from Imperial College, just to show a little bit of loyalty to my former institution. These are third generation solar cells, photovoltaics, where they are engineered to the nearest atom to be very efficient. So you combine indium, gallium arsenide and phosphate in a way they wouldn't normally combine very happily. These things have very different lattice parameters, and so usually wouldn't mix or wouldn't attach very carefully. But you can actually form a so-called quantum well where they all accommodate to each other and form a lattice constant that they're happy with. And in doing so, they form a trap for electrons, and you can use that trap as a very efficient solar photovoltaic device. Sport, all sorts of tennis rackets and things that I really don't know what you do with, full of nanoparticles. Clothing, all sorts of funny textiles. You may have seen socks that never get smelly because they've got silver nanoparticles in them that are killing the bacteria. Sort of an ultra Gore-Tex, so a form of nanofiber that makes breathable fabric so that you stay dry on the inside. Modifying surface chemistry so that it becomes hydrophobic, so that water just runs off and doesn't want to get through. So a lot of this business is actually about coatings and things that we would think of as actually not being particularly high-tech, but actually remarkably powerful when you get it right. And then the one that's just beginning to enter into the consciousness of people who are alarmed about this is food. I think most of us would probably say we would at least like to know if we're eating nanoparticles. At the moment, it's largely confined to the packaging. So things like putting gas-proof layers on plastic bottles and plastic wrappings for food so that oxygen doesn't get in and spoil the food. Or giving the packaging a bit of smartness, so little sensors built into the packaging that detects either the presence of oxygen, which means it's going to go off more quickly, or possibly detects the presence of salmonella and just turns from green to red, that sort of thing. So this is sort of on the edge of reality. In the future, we might be looking at a slightly more advanced form of nanotech, things like little nanoparticles that deliver vitamins, things like omega-3 and other good nutrients that would, to put them into the food naturally would cause the taste to be spoiled. You know, if you fill your food with omega-3, it tastes of fish. But if you nano-encapsulate them, you get all the benefits of the omega-3 without a taste of a fish. And things that can delay digestion. A lot of the good stuff is actually destroyed in the early parts of the digestive tract through the stomach acid and things like that. If you can house the nutrient in a little protective nanoshell, then it gets deep into the colon and can be used for preventing colon cancer and things like that. There's a lot of discussion going on as to exactly what level of information is needed, what level of testing is needed. We can talk more about that later if you'd like to. Okay, let's switch from all the good news story. Let's just talk about one of the flies in the ointment. Two really interesting books that impinged on this subject in the last couple of decades. Now, this book by Drexler called Nanosystems, which was essentially his PhD thesis. And it's a serious book. This is a proper bit of science. And he tried to essentially write the engineering manual to describe what a nanofabrication factory would look like. I mean, he was absolutely years ahead of the game with this, so he was really dealing with a blank sheet of paper. But, you know, if you wanted to build a factory that could build nanostructures, atom by atom, from the bottom up, what would it take? And that book is really the description of that. Michael Crichton, who wrote a cracking novel, but it's a novel, talked about a similar world, but which said factory got out of control and started to build other factories that built other factories, and in order to feed themselves, just started grabbing atoms from the environment and essentially started dissolving the world and making this so-called grey goo. But actually Drexler used the word grey goo as well, of where the whole planet is dissolved by this runaway nanotechnology. And unfortunately, in the public perception, the difference between the solid science and the excellent fiction hasn't been quite as distinct as we might have liked it to have been. In a sense, the Drexler idea was built on very solid foundations, going right back to Richard Feynman in the late 50s, who's seen as the father of all of this field. He was speaking about so-called assemblers of machines that could build smaller machines, that could build smaller machines still, and that would get you down to the atomic scale. This is an artist's impression. I hasten to add the nanofabrication factory doesn't exist. But this is what an artist thinks it would look like. It would be a little desktop box, and it would have a number of bottles of primary elements, or primary feedstocks, so things like acetylene, maybe a lump of carbon, maybe a bottle of hydrogen, that sort of thing, really basic stuff. And then inside this machine, you've got essentially Victorian-style workshop machinery, sort of milling machines and lathes and things like that. So here's one this is a little circular milling machine that's knocking off the hydrogen atoms from acetylene to get pure carbon atoms. This thing spins around and the hydrogen atoms get spewed off the edge. This is a little milling machine that's drilling a nanoscale hole. This is an extruder. All sorts of really classical Victorian mechanics, but at the atomic scale. And he argued that if you could build one of these, you could then use it to build smaller stuff, and that this would be the real route into a different type of nanotechnology, one where you've really built using mechanical principles from the bottom up. And it's not entirely fanciful. I mean, this is a moderate quality simulation of a gearbox made from atoms. This doesn't violate any laws of physics. This thing would just about work. And if we look into our own body, the very thing that drives our metabolism, ATP synthase, the enzyme that is used to fabricate ADP, our fuel, is actually a nanomachine. It's you've got a rotor and you've got a stator, and this part of the enzyme spins round and it pulls protons in and physically rams them together and puts 3 in a chain to form ADP. So actually, nature got here long before we even started thinking about it. The fact we're all living and breathing is because ATP synthase is running very happily in our bodies. But nevertheless, some people weren't happy. Prince Charles wasn't happy. And he wasn't happy because of an American pressure group called the ECC group, who were very, very unhappy. This was all around 2003. And this idea that, almost in a viral sense, it was as if nanotechnologists were dealing with something that if they just lost control of it once, it would escape from the lab and would self-replicate, and that would be game over. The same sorts of worries that people who deal with smallpox in the laboratory must worry about at night. Have I got some on me as I go home? Because if I do, it's going to get out of the test tube. So the grey goo Armageddon was talked about. And actually, to his credit, Prince Charles did the sensible thing and asked the Royal Society to set up a commission to actually investigate how much truth there was behind these concerns. Which they did and produced a very excellent report, so there has been a very good outcome from that. But nevertheless, the grey goo label has continued. So even, this is January this year, the idea that nanoparticles could be used in food, which is something we should certainly talk about and discuss, but these are just static nanoparticles. These aren't replicators or anything that could reproduce itself and get out of control. Nevertheless, that was reported as grey goo food laced with nanoparticles. And so, the public perception is a little bit messy out there at the moment. So what are the ethical implications? Safety is clearly the biggest one. We really have to make sure that we're not playing with fire here. Public acceptance is the other side of that. It's no good if it is actually safe, but the public thinks it's not. We really have to make sure that these two things are aligned. There's the wider question that I guess is associated with any new revolution of technology, is who controls it, who benefits from it. Tangential to this whole subject is the very difficult question of human enhancement. There are a small number of people, not really from the nanotech community, but maybe borrowing some of the tools of nanotech, who would really see the human in this form as being very far from what he or she could be, and that a cyborg-enhanced human is really the future of humanity, and that finally nanotech gives us the tools to do that. I'm not going to talk about that because that is a subject in and of itself, but just to flag that is sitting there on the periphery of this whole discussion. And I think equally part of the ethical discussion is the fact that nanotechnology does hold potential solutions to a number of key global challenges, which in and of itself is an ethical issue, and that for us not to take these things up is an ethical decision of really quite some magnitude. Let me just talk briefly about some of these things. So with safety, a number of the scientific bodies have been doing a very good job in trying to separate the hype from the reality. So a very influential report came out of the Royal Society and the Royal Academy of Engineering in 2004 that really asked everybody to take a breath and to work out what is dangerous, which there are some things, and which bits are really so far away that we shouldn't worry about them for quite a number of decades. And similarly, there's been a very useful dialogue between all of the key national academies of the OECD countries in 2007. And very recently, the House of Lords Science and Technology Committee has done a specific investigation into that question of nanotechnology and food. So if that's something that alarms you, you'd like to see what their thinking is, then that's available on the website to follow up. This is sort of trying to condense hundreds of pages of learned report into one picture. The general thrust of all of these safety discussions has been to say, stop worrying about grey goo. In a sense, by worrying about grey goo, you're missing the real problem. Grey goo is as likely as time travel, to quote my colleague Mark Welland. We should not worry about that, but we should actually look at the things that could be dangerous. And the things that could be dangerous fall into the more general category of toxicology. So we shouldn't be worrying that things are going to escape and replicate and eat the earth, but we should be worried that a specific nanoparticle in a specific situation is toxic to the human body. And what about the workers in the factories who make those things? Do they get a higher level of exposure? What happens if there's an explosion in one of the containers? Is it like nuclear power? Those sorts of slightly more sane, but very, very important toxicological questions are really the heart of the focus of safety here. And it's a two-dimensional axis. It's exactly the same axes people use for laser safety, in fact. You've got to say how much of the stuff is there, and of that stuff, how accessible is it? So for example, having told you that your microprocessor in your mobile phone is a nanotechnology device, are you now going to hold it at arm's length and look at it a little bit suspiciously? Well, no, because actually, if you work out the quantity of nanomaterial in there, it's nanograms. So you've got to say, well, okay, what if this was a poisonous, what if this was iron or chromium, something which in and of itself is extremely toxic? If I consumed 0.1 of a nanogram, which is the amount of nanostructure there is in a typical Pentium chip, what would that do to me? The answer is nothing. You'd need micrograms and milligrams before you even notice it at the clinical level. And then even more so, are those nanostructures floating around in the air? Are they kept inside a box? Or actually, are they glued firmly to the surface? And it turns out with microchips, they're bonded with full atomic force to the surface of the silicon. So not only is there a tiny quantity of it, you could never get at it. You would need the same sorts of forces need to snap steel to actually extract those nanostructures from their substrate. So they're both bound and small in quantity. Therefore, that puts them in the safe corner. Things like on the healthcare, MRI enhancement, a really nice use of magnetic nanoparticles is to inject them into the body and then put the person into an MRI machine. And they shine very brightly, and you can use them like a stain to highlight whatever the nasty is that you're looking for. Now, in that case, they are fully accessible. They're free and they're fully absorbed into the body. That's what we want. But again, the quantity is small, so that's relatively harmless. This is the corner where we have to do proper toxicological tests, where there's relatively large amounts and they are free and in a position to get into the body. So the thrust of most of the safety work is on trying to work out what is the, in toxicology terms, the LD50, what's the dose needed to kill 50% of the population, and then work out how far away we are from that and whether you could ever consume that level of dose anyway. Public acceptance of nanotechnology, there's a very nice thing called the Eurobarometer, which is the European Union runs, and is a survey of public opinion on acceptability of different technologies. This is the state of play about 4 years ago. So nanotechnology is there. So 40% of the European population thought nanotech would improve their standard of living, 42% didn't know, 13% thought it would have no effect, and only 5% thought it would deteriorate their standard of living. It's quite interesting to see where that comes on the scale of things. I think basically the answer in this one is don't know. Most people haven't a clue what it means for them. Nevertheless, you can look at public acceptance. So this is a two-dimensional plot of risk, or perception of risk rather, against perception of benefit. So we like things that are in this corner because they're not risky at all and they're of enormous benefit. And we really don't like things that are in this corner because they're at high risk and not much use anyway. If you want the key to this, I can show you later, but that one's, I mean, asbestos speaks for itself. That one's smoking, that one is alcohol, and that one is DDT, the pesticide. So you really don't want to be sharing company with this corner. This is where nanotech sits. So actually perceived generally as being of medium risk and of medium benefit, and is not entirely out of keeping with other things that we tend to accept. the laser, for example, is there. So nanotech is seen as the same risk level as the laser, but only slightly less useful. So it's an interesting way of just gauging what people think. Then this final ethical dimension of, if we don't do it, let's say the precautionary principle rules, and we just say, well, we can't be absolutely sure, so really the right thing to do is to do nothing. These are some of the global challenges that we will lose a bit of benefit in. So global warming, water availability, limited material resources, energy security, aging population, pandemics, drug resistance, terrorism, and IT access for the developing world. Nanotechnology has some very serious contributions to make to all of these, and I've shown you some of them already today. So it's very much questions that are of enormous ethical importance, not just to the rich or to the consumer, but actually to the third world as well. So finally, what are the religious implications? And this is where I'm really way off territory here. I'm definitely not a professional theologian. So here are a few random thoughts to stimulate further discussion. I just want to ask the question of, is this a new science? One of the things that often happens with anything new, actually, is that there is a drive by the proponents to present this as a new thing that changes all the previous rules. I noticed there's an event in Cambridge next week from Silicon Valley where they'll be talking about economy 2.0. That's quite interesting, the idea that it's a new order, it's a new way of thinking about economy. The old rules don't apply. And certainly some of the proponents of nanotechnology have tried to say, this is new science. The old rules don't apply. It's a very new way of operating, new modus operandi. I think we, as people like me, who are interested in the interface of science and religion, need to ask whether the substantial amount of work that we've done in previous years in understanding how science and faith fit together, whether anything has changed in that dialogue, or whether actually it's business as usual. My personal view is that it's absolutely business as usual. Having been doing nanotech for 20 years, I've seen nothing in there that puts it in an entirely separate class of study. That means that the arguments about, that Christians would use about science is the exploration of the mechanisms that God has set in place, and that as technologists we're encouraged to use these things for the rule and for the care of the creation. Those things still apply absolutely in nanotech, and I see no reason to deviate from them. So I don't think it is a new science. It's got a lot of really interesting things, but it's the same fundamental relationship with religious thinking. On the other side of the argument, I think we should ask, is it a new theology? I was intrigued at a Christians in Science conference the year before last to hear a talk from an anthropologist on nano-creation and invoking nanotechnology as perhaps a middle way between creationism and Darwinian evolution. I've thought about this a little bit, and the argument that was being put forward in this particular talk was that there was a special intervention by God to create nanoscale entities. So essentially God is the master nanotechnologist. And then after that, things then were left to run their course and evolved into larger scale structures, so-called nano-evolution. And then ultimately those larger structures began to decay as per the second law of thermodynamics, which was the entropic evolution. I'm really not convinced about this, I think it has to be said. To my mind, this is intelligent design with the word nano in front of it. I don't see any reason to put the creation of nanostructures at a different philosophical level to the creation of anything else. It really is all part of the same ball games, as far as I can see. Something that I think Christians have to watch out for, is nanotechnology a mitigation of the fall, which I think it is, or is it a new gospel, which I don't think it is. Again, as with all big new movements, there are some people who would like to push them a little bit harder and say they're more than just a string of very nice scientific and technological techniques. Let me just give you a quote from Professor James Czonchevsky, who's actually a serious man in nanotechnology. He's one of the early players and was actually the man who did that abacus that I showed you at the very beginning. You can read faster than I can speak. I'll let you just read that bit. So the argument is that the scientific narrative is one of interdisciplinarity, which is true. Nanotechnology is the meeting place of physics, biology, medicine, chemistry. But he wants to go further and say, actually, it's an entirely new shift in our consciousness and our unconscious minds. He envisages a world where people think across wider lateral planes through nanotechnology and not restricted by conventional thinking. And this is just bordering on the edge of religious worldview, I would say. I don't think he means it too strongly, but I think we can all sense there's just an element there that's one step further than we might be prepared to go. Whereas I think I would want to say that with nanotechnology's ability to address so many of these major global challenges, from global warming through food security, all these things, it is a fantastic tool for those of us who want to do good upon the earth. But it is using things provided by the Creator and is in no sense a substitute for the Creator. There is a salvation narrative, if you like, in some of nanotechnology that is just a little bit overplayed, that the saviour is nanotech, whereas actually nanotech is the tool graciously provided by the saviour. And then finally, I'm way off territory here, but is it the missing link in abiogenesis? So I mentioned this one because Richard Dawkins talks a little bit about this, that in constructing the chain from amino acids through DNA into proteins, at some point you need a way of arranging the amino acids, which are relatively simple to form, I understand, into something more complex, which is harder to form. And that perhaps clay with a nanostructured surface, naturally nanostructured, could form the underlying template that holds the molecules together in the right order. All I'd say about that is I do work in the area of templating in some ways. There are a lot of people in my community who use ideas of templating, and I think that's rigorous. I don't have a problem, actually, with using naturally occurring nanostructure to arrange molecules. That is proper science. There's been some recent work, came out about 3 years ago, that suggested the error rate inherent with that is too great for it to be feasible, and therefore this in and of itself may not be a great idea. I also find that feasible. But what I'd say overall is that in 20 years' time, when we really know the answer, or however long it is, it doesn't really matter from a science and Christianity perspective. Hopefully, we don't hold a God of the gaps theology that's saying, my belief in God is because there's a missing link that science can't prove. When that gap is one day plugged, all we will then have is a more complete description of the mechanisms that God chose in order to bring creation about. So possibly interesting science, but definitely not of great concern. Well, there we go. Let me just recap very, very quickly. So nanotech is the art and the science of manipulating material on the nanometer size scale, and it appears to be on track to form the basis of the next industrial revolution. The industrial processes that nanotech currently uses, or that will be used, will touch every aspect of our lives. People have made the analogy that it's equivalent to Ford's production line. It's a methodology that is applicable to every industry. I've given the example here, everything from computers we use at work through to the sunscreen we wear on holiday. Sunscreen is an interesting example of a nanotech product. I don't think we should worry about grey goo. I do think we should worry about toxicology, and we should make sure it's done properly and it's done early. There are some products out there that maybe weren't tested toxicologically as early as they should have been, and we don't want to go the GMO route. If we handle nanotech properly, and if we communicate it properly so that the public is brought with us, it has the potential to be a significant force for good, addressing many of the modern global challenges that affect both rich and poor, and that those of us who are Christians would very much want to spend our lives addressing. I don't think it changes the relationship between science and religion at all. All it is, it's a clearer view of what God has made. It's nanoscience, and it's a finer tool to tend a garden with, if you like. That's nanotechnology. And finally, we need to remember it's only a tool, it's not a God. Thank you very much.
Thank you, Russell. That's very good timing. Leaves us plenty of time for questions or comments from anybody. So let me throw it open for that. Colin.
Has nanotechnology already been able to store hydrogen in compact spaces?
certainly, so the question was, has nanotechnology been able to store hydrogen in compact spaces? In general, yes. In the specific, I don't know what the state of the art of that research is. The C60 molecules, for example, one of the things that people got excited about there was that in the middle of that cage, you've got place to put other atoms. And so there was a lot of interest in maybe putting hydrogen in there for high-density fuel storage. What I also know is that the general idea of, I guess you'd call them materials far from equilibrium, of trying to really pack things in places where they shouldn't be to create very high energy density states. That's a very active research area at the moment, and it's a one that nanotechnology is addressing quite enthusiastically. Yes.
Thank you very much for a very interesting talk. One of the areas you mentioned, one of the ways in which nanotechnology could help in the developing world you mentioned is water, and I couldn't work out how that could be. Have you? What's being done?
Well, I guess it's twofold. It's partly through renewable energy. So if you have an easily accessible form of renewable energy, you've got the possibility of purifying salt water. But also, it's when it comes to filtration. You can make some, in principle at least, you can make some very efficient filters using membranes with nano-sized pores in them that can be used to remove heavy metals, for example. So there's a lot of work going on in making filters that can clean up polluted water from nanostructures. Yes?
I think I need to know how somebody in your field defines the fall in order to understand this question of how this whole area might mitigate.
Yeah, sure. Sorry, that was a bit of shorthand. So, essentially, as a traditional Christian in terms of theology, my view is that the world is not as was originally intended, and that the reason that bad things happen is because of a fundamental fracture of the relationship between man and God, and that has all sorts of bad consequences. And that the tension the Christian has to hold together is one of saying, well, actually, there has been a salvation, and there will be a salvation, and therefore, in a sense, the present fallen world is not of concern. Hold that intention with the fact that while we are here waiting for that redeemed world, we should really try and patch things up. And it's an idea that's been, I think, universally accepted amongst Christians when it comes to medical work. So Christians for a very long time have believed in medical science and in trying to heal. There's been a bit of a divide of late as to whether the same principles equally apply to the environment and things like that. Personally, I see those as the same class, that if we're prepared to build hospitals, we should also count our carbon footprint. And it's in those areas, through nanotechnology's ability to create, hopefully, renewable energy, and I guess to show compassion to people who are suffering in the fallen world. That's how it's a mitigation.
Presumably going to become helpful at some point to actually create self-replicating nanotechnology machines, which is what the grey goo fuss is about. But I would have thought that one of the simplest ways of avoiding it becoming a danger is to make it entirely dependent on some relatively or very rare element, such as boron or platinum, so that if it does escape, there's no way it can actually take everything over.
I mean, I think I'd want to challenge the premise of the question, actually. I don't think there's that much interest in building a replicator. People talk about the need for a Manhattan project, a major international effort to build the first replicator. One of the things the Royal Society commented on in their 2004 report was that of all the industrialists they spoke to, nobody was particularly interested in the replicator. So industry doesn't think it's the right way forward. I think I can relate to that as well. I mean, in very simple terms, there's always a trade-off between flexibility and efficiency. The replicator is the world's most flexible machine, and therefore, at a first pass, I would say it's probably the world's most inefficient machine as well. And certainly building things atom by atom is a very tedious way to go about things. So you may find people who disagree, but I'm not convinced actually there is much of a drive to try to produce these things. I guess, yes, I mean, it would be interesting to try and put a safety limit in like that, although you've got to be careful that safety limit would hold. I mean, if you're in the style of the replicator, you're really taking individual atoms and shoving them together, you might be able to do things that you couldn't do in normal chemistry. And so the normal rules of chemistry about which materials are safe and which ones will react with which may not hold anymore. It's difficult to tell.
But actually the stronger drive might be that companies want to make profit, and so they don't want to give something to somebody that can go away and replicate itself, because they want to keep control of it, which is exactly why GMO manufacturers put stop genes in their genetic seeds, so that you have to keep buying them every year. You can't just do what my dad did and take some peas and put them in the drawer and plant them next year.
More likely to possibly be used in either space exploration or exploration of inaccessible places on Earth.
That would be a better use. Or military use, which is what would inevitably. Yes?
Brian, he gave a lecture last night about playing God, and there's a lot of overlaps with his talk about stem cell research and synthetic biology, in the sense that you've got this new granularity, as you've said. This is the power to address things at a far stronger and deeper level.
Yeah.
I've been talking for some time about the global problem of challenge of nuclear waste, and perhaps the solution might be to put it at the edge of the ocean, where the tectonic plates are subducting underneath the continents. Do you think that there is anybody looking at encapsulating nuclear products, plutonium and such, in this level?
I'm not aware of anything. Doesn't mean to say it's not happening. It's not on my radar.
It's being done in my department with clay minerals of various kinds.
Right.
And putting them into a subduction zone is a really bad idea, because everything that goes down comes up again. In volcanoes, actually. So people did look at that about 20 years ago, and unfortunately they decided it was not a good idea. There was a question here.
You've described a whole lot of beneficial applications or potential applications. In general terms, are there any specific things that you think people are planning to do that you would consider ethically misguided?
I guess there was one actually I intended to flag and didn't, and that's in the area of catalysis. And I don't say this in order to attack that particular industry, but it's an example of how there can be flip sides. So for example, one of the reactions you can catalyze using nanostructures is the conversion of coal into oil. And there are many countries have very large coal reserves, which currently are not particularly interesting as a fuel source because they're too expensive or too difficult to access. But if you could catalyze the conversion into oil, for example, it would change the market dynamic. And that would put a lot more carbon dioxide into the atmosphere. So that's an example of how it's not all good.
For some of us, knowledge of these amazing little machines at nano level, which make ATP and so forth, are very strong arguments for an element of design in evolution. You did show a slide which related to that, but I didn't quite gather your own view. Was it that up to that stage it was sort of set up by the Almighty, and after that chance methods led to the evolution we see today? Or what was the...
That wouldn't be my view. That was the view of the presenter that I was reporting. It's not a view that I hold to. No, I take a theistic evolution view with no intelligent design.
You believe you can get to that stage of these wonderful machines purely by Darwinian, well, you misquoted Darwin, of course, but by purely rotatory methods, if you can call them methods, chance effect.
I think I can say yes to that, as long as in saying yes, that doesn't in any way undermine a full belief in God the Creator. I mean, this is the point of theistic evolution, that...
You have a creator, you've got to create something, isn't it?
Absolutely, but the mechanism by which he chooses to do it doesn't have to be quite as directly cropping in situ as we might think it is. So my personal view is that Darwinian evolution and all the other forms of evolution that would lead to those sorts of structures is the glorious mechanism that he's chosen to implement his creative will.
Let's thank Russell again very much.